Alright guys, we're going to talk a little bit more about parabolas today. And first thing I want to do is I want to look at an example where what we have going on is we know the vertex of the parabola. We know some other point that it goes through. But we don't know that this point is any special point. It's not straight across from the focus. It's just some other random point the parabola hits. So in this case, we know the vertex is -2, -4, +4. We know this point is -3, +2. And so another thing we know, since this parabola opens down, we learned before if parabola opens up or down, that means it has to be an x squared. And so from what we saw with the standard equations before, we know this has to look like this. We have to have x minus h, the quantity squared, equals 4a times y minus k. But there's something else that we can put in there. We know h and k because we know the vertex. So I'm going to put in both of those points. So this becomes x minus -2. So I'm just going to say x plus 2. The quantity squared equals 4a times y minus 4. All right, and then to figure out what the rest of this should be, we need to figure out what a is, basically. Now, to figure out what a is, we do have a point that has to work in this equation. So basically, this is an xy, since it's on the graph, that needs to work in this equation. So really what I'm going to do is I'm going to take this point, put it in for x and y, and then see what that makes a. That's going to leave a my only unknown, my only variable. So I'm going to do -3 in for our x. We've got -3 plus 2, the quantity squared, equals 4a times, we've got 2 for our y coordinate, minus 4. All right, so let's just solve each of these parentheses first. Don't forget like PEMDAS while we're working through this. Parentheses first, then exponents, then multiplication, all that good stuff. So we've got -3 plus 2. We've got -1 squared equals 4a times 2 minus 4. So we've got -2 there. All right, -1 squared is really just +1. -1 times positive, or -1 times -1 is +1. And we've got 4 times a times -2. Remember, this is all multiplication here. And so 4 times -2 is a -8a. All right, and then to get a by itself, I just need to divide both sides by -8. And when I do that, I get that a is -1/8. You know, that's not a super nice number, but that's okay. It's just whatever it works out to be. And so remember, though, we need to get our equation in the end. It's not just what is a. The question is find the equation of the parabola. So if we want the equation in standard form, basically, I want to go back to basically what I have right here, more or less, and I want to plug in that -1/8 for a. And so that's going to look something like this. So I'm going to have x plus 2, the quantity squared, equals 4 times a, but now I know a is -1/8, times y minus 4. And then just to take it one step farther to finish this off, if we've got 4 times -1/8, then basically 4 times -1/8 is just -2. So in the end, I've got x plus 2, the quantity squared, equals -2 times y minus 4. There's the equation of that parabola. Has a vertex at -2, +4, and making a -2 makes that point work. And so now we've got the equation of the parabola that has everything happening that needs to happen in that particular. All right, next up, I got one more thing I want to do here for another example. That's find the vertex, focus, and directrix of this parabola. Now that's not too bad if a parabola looks like this. We know the vertex is hk, and 4a right here is going to tell us how far we need to go from the vertex to the focus if I just divide this number by 4. The problem on this one is this isn't in that form. It's not in what we call the standard form of the equation of a parabola. It's in general form. And so we're going to have to do some work to make this fit that standard form of a parabola. Now, the very first thing you should look for is the x squared or the y squared. In this case, the x is squared. So we're going to want to make it fit that model right there. If the y were squared, we'd make it fit the other one where basically the y minus k and the x minus h are switched. So this want to make that equation look like that. So what I'm going to do first, it might look a little weird. I'm going to write a real similar equation. I'm just going to leave a gap after the 8x. There's a mathematical thing that we've already talked about this year a few times, where if I want to get this to where it factors as the same thing twice, you notice my goal is to get a quantity squared for the x's. We have a mathematical thing that does that, that guarantees if I add the right number here, it's going to factor as the same thing twice. And if you don't remember what that was called, it was called completing the square. And the method for completing the square is you add half of the b term squared. Now, as a reminder of what the b term means, if you have a quadratic, it always goes ax squared plus bx plus c is this constant here. So the b term is basically the part that's on the linear. So the x to the first, that's our coefficient, that's b. And so I need to take that, that's our b, take half of it, and then square it. That's the number I need to add. And so if I take half of 8, that's 4, square that, that means I need to add 16. Now here's an important thing. In math world, you can't just like add a number to one side of an equation. You're not allowed to do that unless you do it to both sides. Then that's perfectly okay, right? So since I added 16 to this side, in order to make this stay an equation, stay equal, I need to add 16 to the other side. All right, so now that's perfectly okay that I added 16 because I also added 16 over here. So let's see if we can factor this. Now, quick review on factoring. If I want to factor a trinomial like this, basically I want to find two numbers that multiply together to give me 16 and add up to 8. So 4 and 4 would do the trick here. And so I'm going to have x plus 4 and another x plus 4. That's how that side would factor. And then over here, all I'm going to do is put together these like terms. You just have a minus 8 and a plus 16. So if I have minus 8 and plus 16, that's really the same thing as just plus 8. All right. Now remember our goal. Our goal was to make this look like that. I need to have a quantity squared on the x's. So basically, that's what I've got here. Squaring a number is multiplying a number by itself. So I have x plus 4 times itself, which means this side really is x plus 4, the quantity squared. And then this side over here, we need to get this to look like a number out in front of y plus or minus a number. Which means basically I need to get rid of this 4 in front of the y. And the way to do that is basically factor it out. So I need to factor, and remember, factoring is really just division. And so if I factor a 4 out of both of these parts, I have left just a y there, because 4y divided by 4 is just y. And then 8 divided by 4 gives me 2 for that part. And so now this looks like a form that we can work with. So this is now in standard form from general form. So we've got this in the format we want, where we can find the vertex, where we can figure out what A is, and then from there we can figure out the focus and the directrix. So to find the vertex first off, the vertex is just h and k. So h is negative 4 technically. Remember, it's minus in the standard equation, so the vertex is the point negative 4, negative 2. Now I'm going to draw a little picture off to the side here because I feel like it's helpful. Graphing this wasn't actually part of the question on this one, but I still feel like it's valuable to see what's going on this. So we've got negative 4, negative 2 for the vertex. So right there is our vertex. So once we have that, to find the focus, we need to figure out what A is. And remember, A is dependent on this number right here. That part is 4A. So in other words, on this one, 4A equals 4. That means A must be 1. Now the x is squared, which means this either opens up or this opens down. The fact that it's positive for A means this opens up. So that means to get from the vertex to the focus, remember that's what A stands for, is that distance. And so distance from vertex to focus is 1 unit up. That's the way this is opening, and every single parabola opens around the focus. And so that means the focus is that point right there, and so to put it over here, If I just went up 1 point from there, that's the point -4, -1. And so our parabola is going to look something like this. I didn't like go through the work of the lattice rectum to figure out exactly how wide it was because graphing it wasn't actually part of this. The other part that we're supposed to find though is the directrix. Now remember, however much I go to get to the focus, I have to go that same amount but the opposite direction to get to the directrix. So I went 1 unit up to get to the focus, which means I need to go 1 unit down to get to the directrix. And remember, the directrix is not a point, it's a line, which means the directrix is this horizontal line that's down 3 units. And since it's horizontal, it's going to be the line y equals -3. All right, so does that make sense how we got that? So big things to remember there. If you have something not in standard form, we're going to put it in standard form. The way to accomplish that is completing the square. And so we're going to leave a space to add in our c term in the ax squared plus bx plus c, like a quadratic. And the term that we want to add is always 1/2 the b term squared. That's how we get the correct number, so it will factor as the same thing twice. And remember, if you add it to the one side, you got to add it to the other side to keep it equivalent. All right, and then from there, just simplify until you have it in standard form. And then from this point, it's really what we did yesterday. We can find the vertex, focus, and directrix from knowing what A is and knowing what H and K are. All right, I've got one more thing that I want to talk about a little bit today, and this is just kind of like the application of parabolas. Because a lot of what we've seen so far is stuff with graphing parabolas, the standard equation. We haven't seen a lot of like why people care about parabolas. Um, and so earlier in the year, we talked about parabolas as equations and why people care about them with revenue equations, with projectile motion, things like that. But as far as the focus is concerned, there's actually a couple practical applications for that as well. And so I just have just a basic parabola drawn here. There's our vertex, there's our focus. A really interesting property that a parabola has is if something comes in and bounces off the parabola, it will go directly to the focus. And so you can kind of see this from this picture here. Like if something comes in, like at that angle, it's going to bounce off and go directly to the focus. If something comes in way up here instead, it's still going to bounce off and go directly to that focus. There's a rule in physics that says basically an angle of incidence, the angle it hits at, is the same as the angle of reflection. So the angle it hits that curve at would be the same as the angle it leaves it at. And if everything does that, it doesn't matter where it hits this parabola, it all comes back to the focus. Now that's really handy for a couple practical uses. One big one is satellite dishes. So if you have a satellite dish, the way this works, there's a receiver out here, and that receiver's out here because if anything, if the signal for the satellite hits this satellite dish anywhere, then it's going to reflect off and go directly to that receiver. Otherwise, if this wasn't the case on a satellite dish, every single time the wind blew and shook the satellite dish at all, you would lose your signal. And so they're made like this so you can have a little bit of a jiggle, and as long as it hits somewhere in that parabola, it's going to bounce to the receiver and it's going to be okay still. And this one here in particular, I'm hoping I can post a video where I get to use this. I wanted to bring this to school, but since we're out right now, I don't know if that's going to happen. If we get some sunshine, I know that's a tough thing to come by in Ohio, but if we get some sunshine, then I'll take this outside and I'll post a video of me using this to catch some things on fire. Basically, this is a satellite dish. It's just reflective material on top. And since this property works, it can concentrate all the rays of the sun and create something I like to refer to as a death ray, which is fun. And so there's one big property of these. And the same thing kind of works the other way around. If something leaves the focus and goes out and hits the parabola, it will actually hit the parabola and all leave the same direction. So I want to show you this with a little mag light I've got. And so this is basically just a flashlight, but if you've ever used a mag light, you've probably noticed that you can spin this around and it changes the beam of light. Basically, all that's going on here is inside of this, you've got a parabolic reflector. And so basically what this part is right here is just a mirror that's shaped like a parabola that's been spun around. It's called a paraboloid of revolution. So you take like a 2D parabola and you spin it full circle to make a 3D shape. Um, and so if you move this, the beam gets smaller, then it gets bigger. If you get this right to where the beam's as small as it could be, basically what you're doing is you're putting the bulb in this, the light source in this, right at the focus of that paraboloid of revolution. And if you do that, it creates this beam, this solid beam of light. And this is the way they make searchlights. You've ever seen those lights at like haunted houses that shine clear up onto the clouds, the Batman symbol, things like that. Basically, this is the idea behind that. You just take a light source, put it right at the focus, shine it onto a reflected surface, and they all leave going exactly the same direction. Um, and then just one last application I wanted to mention is this. If stuff hits the parabola and goes to the focus, you probably noticed at football games how you can always hear the quarterback like yelling out the cadence, and then if you've ever wondered like how do they get that audio, and then they snap the ball and you hear everyone's helmets crash together and things like that. It's really just based on this idea. Watch the next time you see a football game on TV. There's usually people on the sidelines holding things that look basically like satellite dishes, like clear satellite dishes. And right at the focus of that satellite dish that's actually a paraboloid of revolution, there's a microphone. And so basically what happens is whenever that sound comes from the field, if it hits anywhere on that parabolic reflector, it goes right to that microphone. And that's how they're able to pick up that sound from really far away and hear all the helmets crashing and stuff that you like to hear when you're watching a football game. And so, and there's some other cool stories about this, and I could talk about this for a long time, but just one last one. There's actually a myth, and maybe it's true, I don't know, that Archimedes back in the day had his soldiers shine up their shields and stand in a parabolic formation. And then, whenever the Romans came in to try to take Syracuse, which is where Archimedes lived, when their ships would sail in and sail through the focus of that parabola, their sails would catch on fire and it would burn up the ships before they could ever make it to the harbor. Is it true or not? I don't know. But Archimedes definitely would have known the mathematics to do it, which is pretty cool. And so there's a lot of kind of neat applications of this as well. So that's just some other things that have to do with the parabola. And so this is the kind of the stuff that we're going to be using here. I'm going to put a question or two that has to do with this idea on you guys' assignment as well. But most of the assignment's going to have to do with the first couple examples that we had. And so that'll wrap it up for parabolas. Next to come, we're going to start to talk about ellipses, our next conic section.